Okay, imagine, well, one of the things we have to do in this unit is be able to draw the field lines for different charge configurations. So the first example we'll see is what we call an electric dipole, which is one negative and one positive charge. Field lines we know point where a small positive test charge would go if released. So if I took a small positive test charge and I put it right here, it would just go straight across. The positive test charge would be repelled from the positive source, and it would be attracted toward the negative. So it would go straight across. If I put it right here, it would be repelled from the positive radially, right? So it would start traveling out radially along some radius, and then it would be attracted toward the negative along the radius. So it would start out by moving away from positive on a radius, and it would come in on a radius toward the negative. And so here's what the field lines would end up looking if we drew them at all points, right? Starting at a lot of different points. So we would produce this bow tie or spider looking shape. Imagine we have two positive charges like this. If I put a test charge, a positive test charge right here, it'll be repelled from the positive out along a radius. So it'll go out like this. But then as it travels out, it starts to get pushed away by the other positive. So it goes up and then sort of off and away like this, right? And here it would be pushed off and away, off and away. And here's what those field lines would look like. Now, at some point P, right here, smack dab in the middle, the electric field strength would be 0 as long as these two positive test charges were the same. And everywhere along a vertical line in the center, everywhere along a vertical line, the E field would cancel out due to the two individual test charges, and there would be a net E field of 0. Okay. So what if we have two oppositely charged parallel plates like this? This is different from other situations that we've seen. Okay? Two oppositely charged plates will produce what we call a uniform electric field. So all of the field lines will be parallel inside in the space between the two plates. And of course, field lines point from positive to negative, so we'll just have these vertical lines pointing down from positive to negative. Now, the field strength everywhere inside will be the same, so no matter where you go between the plates, you'll have the same field strength. It'll look like this. Now, I said that these would be parallel lines, but at the edges, we have this bowing effect. They bow out at the edges. Okay? So what that shows us is that the field is really only uniform kind of in the middle between the plates, in the middle region between the plates. And at the edges, because the plates end, the field starts to bow out and it starts to look more like the electric dipole, where it moves out along a radius and then comes in along a radius. So whenever we draw this picture, right, the field due to oppositely charged parallel plates, whenever you draw it, you have to include this bowing effect where the fields start to look radial again. Right? You have to include this in your drawing because that's what happens at the edge. If we have a charged hollow sphere, which is positively charged, or if we have a charged sphere which is filled in the middle and positively charged, we know how to draw those field lines. They look like this. They start at the surface and they extend out. Now here's something we haven't discussed. We haven't talked about what happens inside. But first, let's see if we have a negative sphere, right? Whether it is hollow or filled, it's the same picture, but the field lines terminate at the surface. When you draw this picture, it is crucial that the field lines start at the surface. Do not start your field lines at the middle. That would be wrong. And here's why we don't start the field lines in the middle, right, at the center of the circle. The reason is because there is no electric field inside a charged hollow sphere, and there's no electric field inside a charged filled sphere. E is 0 inside a sphere. And likewise for negative. there is no field inside. Now, imagine we want to plot the electric field strength as a function of r, the distance from the center of the sphere. Right? So remember, r is measured from the center of the sphere. Well, here's the radius of this sphere. It's big R. So let's mark that point on the axis. You will get an inverse square curve like we've seen. As I move closer and closer and closer, right, as r, little r decreases, as the distance from the center decreases, the field strength increases, increases, increases in the inverse square way that we would expect. But then once I pass inside the surface, once I'm inside the sphere, now, as long as little r is less than big R, right, the field is zero because E is zero inside a sphere. So the graph drops down and is zero at all points below R, big R, right, because the E field inside a sphere is zero. So in our equation for electric force and in the equation for E field strength, there's this constant K, but the thing about the constant K is it's only equal to 8.99 times 10 to the 9 when we're dealing with a vacuum. We could actually calculate K using this equation. K is equal to 1 over 4 pi times epsilon sub 0, and epsilon 0, right, epsilon naught, is called the permittivity of a vacuum, or we could call it the permittivity of free space, by which we mean empty space. Now, the permittivity of empty space, of free space, isn't exactly equal to the permittivity of air, but the two values are very, very close. So whenever we're dealing with problems involving charges placed in air, we can use this value of K and get a very accurate answer. So you might be wondering, what is permittivity? What does it measure? Right? What does it mean? What's the meaning of permittivity? Well, think about this. When you take a charge and you put it in empty space, the field just propagates out through the empty space. But if you put a charge in a medium, well, now the field is propagating through particles of the medium. And particles themselves have charges. They have electrons and protons. So when the field propagates through the medium and through the charges, through the particles, those particles of the medium become electrically polarized. And what this means is that they produce a small counter field inside the medium, which opposes the electric field of our source charge. Okay? So we took some source charge, we put it in the medium, and now we have polarized the medium, and we have a second opposing field, right, which opposes the primary electric field of the source. So this counter field is measured by permittivity. Permittivity of a medium, epsilon, permittivity is epsilon. Permittivity measures how much the medium will become polarized, right, and how much will it resist or produce a counter field. How much will it resist the electric field? And it's a value that we're not going to deal much with. We just have to know that whenever we're using this equation, we are assuming that the permittivity is equal to the permittivity of free space. Whenever we use this value, we assume that we are in a vacuum. We assume the permittivity is the same as in a vacuum. Now, we know charge does not flow freely through insulators. In physics, we say the reason is because insulators don't have free electrons. Now, the chemistry explanation would be, in a plastic, the electrons are locked into place because of the valence shell configuration. Right? Specifically, the valence shell is nearly full in the plastic atoms, so the atoms hold very closely. They hold tightly on their electrons. In a conductor, on the other hand, we have lots of free electrons, and in physics we say that's the reason why charge flows freely through a conductor. In chemistry, we know that the electrons in conductors like metal, right, the electrons are loosely bonded in a sea of electrons. And so the loose bonds allow for the free flowing of electrons through a metal. So insulators don't have free electrons, and conductors do have free electrons. Examples of insulators are plastic and rubber. Conductors include metal, especially copper. Copper is really, really widely used as a conductor. And the human body, we also say, is a conductor. Now, what about the earth or the ground? Oops. The earth is an infinite source or sink for charge. And what that means is that we can put a lot of charges into the earth and the earth will remain neutral. Or we could suck a lot of charges out of the earth and it'll still remain neutral. And the reason is because it has so much more charge than anything else in our world, right? There's nothing in the world that has as much charge as the earth. So we could suck a lot of charge out of the earth and it'll still remain pretty much neutral. Or we could put a lot of charge in and it'll still remain neutral. So imagine I take a ride, okay, and I rub it with cloth. And you might know that doing this produces a buildup of electrons, an imbalance of electrons on the ride. So for example, if you take the rod and you then connect it to the ground, all of those excess electrons, they want to move to a position where they don't feel this strong electric repulsion. In the rod, they're really close together, they're built up, and they repel each other. So they want to move away from each other so that they can neutralize. And they do that by flowing into the earth. So if you take a rod and you connect it by wire to the ground, the excess electrons in the rod will flow into the earth and they will neutralize in that way. And the earth will still remain neutral because of its huge size, because it has so many electrons and protons. So it can accept an infinite number of electrons and still remain neutral. It accepts the electrons from the rod. And likewise, it can also give an infinite number of electrons and still remain neutral. Now, even though plastic is an insulator, we can transfer charges to a plastic rod by doing what I just talked about. If you take a plastic rod and you rub it with a cloth, we will put charges onto the rod. So here's what happens. When we rub a cloth against the plastic rod, we place the electrons of the cloth very, very close to the plastic atoms. And we know that plastic atoms pull very strongly on the electrons. Cloth atoms, on the other hand, don't pull so strongly. That's what makes cloth kind of a conductor, right? Because it has free electrons. Plastic atoms pull strongly on electrons. So if you put the plastic near the plastic will pull the electrons off of the cloth and will have a buildup of electrons on the plastic. So if we then take away the cloth, right, if you rub the rod, you remove the cloth, the charge imbalance will remain on the rod. Since the plastic is an insulator, the charges can't flow anywhere because they can't flow through the rod because plastic is an insulator. On the other hand, if we had a metal rod, then the excess electrons on the rod that we just put onto the rod, they would flow through the rod, through the hand and the body of the person holding the rod, and they would flow into the earth, leaving the rod neutral. Now, the last thing we're going to do in this video is compare electric force and gravitational force. The big similarity between the two is they both follow what we call an inverse square law, right? Which means the force is proportional to the inverse square of the separation distance. The difference is, well, gravitational force is always attractive, whereas electric force can be repulsive. And the other thing is that gravitational force, as it turns out, is a much, much weaker force than electric force. If you compare the gravitational force between two protons, it's way, 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 way smaller than the electric force between the two protons. So gravitational force is much weaker than electric force.